Hello, folks, and welcome to the Tutor's Guide to Math, where we talk about everything and anything related to math. Today, we're going to be getting into some algebra stuff, specifically the entire unit on exponential and logarithmic functions. This is a really long topic. I'm going to be breaking this up into several parts, but it needs to be discussed. We need to go through each little bit here. And the place to start with this is something called inverses. So hopefully, as a prerequisite, you've already learned about composition of functions, and hopefully you have some sense of how to graph parent functions for various graphs. I'm not going to talk very extensively about inverses here because they really only have a slight bearing on what's going on, but I do want to discuss this. So I want you to imagine that the machine that you are feeding things into, we're going to call it f of x, right? And we take some number, x, and we feed it in, and out on the conveyor belt comes a different number, which we'll call y. Now, when you do composition of functions, what ends up happening is you feed this result into a second machine, a second function, right? And when you do this, this is how you get f of g of x, or in this case, g of f of x. And so when you do this, you're going to get, another number coming out here. So I could call it anything I want. We could call it, for instance, z. The deal is when you are using two functions that are inverses, the end product is the same as what you started, which is to say that z is just x. So, whoops, this is the wrong color. Give me a different color, please. Zoom. So this is now just x. So what we conclude from this is that the f machine turns x into y. The g machine turns y into x. So in essence, they are opposites. Now, I like to use the word opposite very lightly here. I prefer to think of it as they are backwards versions, or g is the undo function for f. It reverses what f does. And you're going, okay, well, why does this matter? Well, these are actually super important in general because what they mean is that you can strip away some process. I want you to imagine you've got 3x equals 18. How do you solve that? Well, you divide by 3, right? Why? Because right now what happens to x is it's being times by 3. You need to unmultiply it by 3. How do you unmultiply by 3? By then dividing by 3. They are opposite processes. They are inverses. They do the opposite. So you're very familiar with quite a few of these. The inverse to multiplication is division, and vice versa. The inverse to division is multiplication. The inverse to addition is subtraction. The inverse to squaring is square rooting, sort of. We have to be careful with that one because there's some issues with negative numbers. But basically, you do one thing and then you do the other, and they flip-flop. And this is a very, very important concept to understand because it is going to be at the entire heart of the second half of this unit, which is the logarithms. Logarithms will make absolutely no sense whatsoever. They will look like this weird shell game, put numbers here, do this over there, and hocus pocus, there we go, if you don't understand how an inverse works and what it is good for. So inverses are extremely vital There is an entire lesson that we could be having on inverses. We could be talking about solving, oh, well, f inverse of x is equal to x. And the same is true in reverse. F inverse of f of x is equal to x. And we could talk about the graphs and how they are reflections across the line y equals x. We could get into how to find an inverse by switching the x and y in an equation and then solving. There's a lot that can be said about inverses, and really it's an own entire lesson. But I want you to remember this inverse thing because I am absolutely 100% coming back to it later. Okay, let's set that aside. Let's talk about exponential functions. An exponential function is a function that has the variable in an exponent. That's it. So for instance, if we said y equals 2 to the x, it doesn't even have to be y equals though. It could be 9 equals 3 to the x, for instance. And so anything that's got a variable up top, this is very different from your polynomials, right? If I had said 9 is equal to x to the third, you're going to solve this very, very differently. The inverse to cubing something is going to be the cube root. But we can't do the xth root here. That doesn't make sense because how do you do that? Yeah, you could say, oh, well, if we could take the xth root, it would be the xth root of 9 is equal to 3, but that doesn't solve anything. It doesn't get x by itself. Like, what does that do for us? So we don't want to take that approach. So we're going to have to find some other ways to handle this. So for starters, we're going to say, well, what about when we can just solve it by eyeballing it? So for instance, what if we said 9 equals 3 to the x, just like I wrote a second ago, and we go, well, 9 is 3 to the second power, 3 squared. So if 3 to the second equals 3 to the x, obviously the x value that will make these two statements the same is when x equals 2. And so you can play this game and you can solve a lot of equations this way. And typically, your first lesson in this chapter, other than the one on inverses, because most teachers do start with inverses in this chapter, um, the first thing that gets into exponentials is typically going to involve solving expressions like this. So we would have, for instance, 4 to the x equals 64. And you have to think, is 64 a power of 4? And in fact, it is. 4 times 4 is 16. 16 times 4 is 64. So this is equal to 4 to the third power. Therefore, x is equal to 3. I strongly recommend that you know all your squares up to 15. 15 squared is 225. Know all the numbers up until that point. Know your cubes through 5. 6 isn't bad to know as well. And know powers of 2 up to 2 to the 6th equals 64. And the reason I say this is because your teachers will tend to use these things over and over and over again. Also recognize how powers of 10 work. That the number of zeros is equal to the power. By that I mean, like, if you have a million, which has 6 zeros, that's the same thing as 10 to the 6th. This will make it a lot quicker for you to solve these questions and to recognize what's going on. But let's do a couple quick examples here of other situations that you might encounter. So let's suppose we have 5 to the 2x is equal to 125. Now, what I'm recommending you know is that 125 is 5 cubed. So it means 5 to the 2x equals 5 to the third. If the bases of the exponents match, the exponents themselves, the powers must match. So this must mean that 2x equals 3. and therefore x is equal to 3/2, or 1.5. If we were to say uh, 10 to the 3x minus 1 is equal to 10,000, we're going to need to recognize that this is 10 to the fourth. 10 to the fourth, 10 to the 3x minus 1. So 3x minus 1 equals 4. 3x equals 5. X is equal to 5/3. Okay, that's one variant. There are a couple other things I want you to make sure that you remember when you're doing these, though. First of all, let's remember how negative exponents work. If I were to say 7 to the x is equal to 1 over 49, well, 7 to the x is equal to 1 over 7 squared, or in other words, 7 to the x is equal to 7 to the negative second power. Because when you have something in the bottom of a fraction, it's like writing it in the top, but with a negative exponent. And the reverse is also true, by the way. Let's not forget. If something's in the bottom with a negative exponent, it's like writing with a positive in the top. But in this case, we will conclude that x is equal to -2. I could do this with 1 over 49. I can also do this with decimals like 0.00001. I can write that as 10 to the negative something. I wouldn't be surprised if you see a question like that in class. But the other type of question that gets confusing is when they start mixing the bases. So for instance, what if I said 9 to the x is equal to 27 to the x minus 2? Okay, wait, what? Huh? In these other questions, in the ones that we did out here and out here, we wrote it so that it was an exponential expression equals an exponential expression, but they all had the same base. And because they had the same base, we could just go, oh, so clearly the numbers on top must match. We can't do that here. 9 is not 27. 27 is not 9. But can we make them the same? One thing that you should know, again, because you're going to learn your squares and your powers of 3, or your cubes up to a certain point, is that 9 and 27 are both 3 to the something. Specifically, 9 is 3 squared and 27 is 3 cubed. So if I write this as 9 to the x equals 27 to the x minus 2, now this is something we can work with, because if you know your exponent properties, you know that power to a power means multiply. And so this is 3 to the 2x equals 3 to the 3x minus 6. Oh, now we can say that our bases match. And now this is just like all the other questions. So now we can say that 2x equals 3x minus 6. And consequently, we'll add 6 to both sides. We'll subtract 2 to both sides. We get x equals 6. Ugh. All right. One more example like that. Let's suppose that I say 4 to the 9x minus 3 is equal to 16. Or no, I don't use 16 because 16 is a power of 4. 8 to the 6x plus 1, just to make random numbers up top here. Okay, so if I'd used the 16 like I originally wrote, I could just go, oh, well, 16 is 4 squared. And then we could have said 4 squared, 2 times 2 times 6x plus 1, and called it a day. But now we got to mess with both sides. We got to go, what do I do with the 4 and the 8 to make them match? And the answer is we're going to treat them as both powers of 2. 4 is 2 squared, and 8 is 2 cubed. And I just realized that I used numbers that are probably not going to work out here. Oops, what am I doing? 6x plus 1 And so if we now do our power to a power, we get 2 to the 18x minus 6 is equal to 2 to the 18x plus 3. That means that 18x minus 6 is equal to 18x plus 3. And if I subtract 18x from both sides, I get negative 6 equals 3. What? Okay, pause for a second. In what universe will negative 6 equal 3? Can you come up with an x value that will make this statement true? Is there any number for x we can plug into negative 6 equals 3 to make the two sides match? Well, obviously not, because there's no x here to even do anything with. It can't affect it. So either this is a universally true statement and it's all solutions, or in this case, there are no solutions because there is no number that will make this true. So, whoops, I made a bad question, but that's okay. It's good as a learning tool. So this right here is a whole slew of stuff you are going to see in this first lesson on exponential functions. Okay, so that's great. That's just fine. But we have to ask ourselves, what if we can't do this? Like, okay, it's great and all that 3 to the third is 27 and 3 to the fourth is 81. So if I asked 3 to the x equals 27, you know the answer. And it's great that if I ask 3 to the x equals 81, you'll know the answer to that too. But what happens if we pick anything in between? So this is where the inverses come in. We need to find an inverse process for exponential expressions. And as of right now, we do not have one. It doesn't exist. We have absolutely no idea how to reverse 3 to the x equals 50. So what we're going to have to do is we're going to have to just say, well, whatever this reverse process is, let's make it up and give it a name. And that is exactly what the dude who invented these things did. Fellow in the 1600s named John Napier. He was an astronomer, and he was constantly dealing with these astronomically large numbers where it was like 10 to the x equals some ridiculously huge number, and he needed to know what that exponent was. And so he did this in painstaking fashion, creating this long, humongous table where he solved things by hand. If you've ever done a square root by hand, you know what I'm talking about. It's long, it's tedious, it's awful, because he didn't have a calculator that could do this stuff for him. Fortunately, we do. And so these questions, like you're seeing here, where it's not 27 and it's not 81, but it's somewhere in between, this is a calculator question. There is no way to solve this by hand, not realistically, not unless you have a table like the one that John Napier created to go looking up your answer. But what we are going to have to do is we're going to have to say our outside machine, our first machine is 3 to the x. Our second machine needs to be the inverse to that. It needs to be the, the inverse to 3 to the x. And the reason why is because if we do f of x and then we do g of, because they are inverses, we will just get back to plain old x. So we are looking for the thing that will undo this. And as I said, we don't have it, we have to invent it. So we're going to call it a log. Why? I don't know. Just sounds like a good name. We're going to call it a log. And I'm going to write this in like function notation, like f of x stuff. So I'm going to write log of 3 to the x is equal to log of 50. And don't treat that as a multiplication. This does not mean log times 50. This is like f of x does not mean f times x. But if we do this process, log of 3 to the x, what I contend is that this will reduce to just x. X equals log of 50. And that is your answer, whatever the heck that is. We're going to need a calculator to find it. Conveniently, your calculator has a button on the front of it, most likely, unless you have a really basic calculator, that says LOG on it. That will actually not give you the exact right answer, and we'll get into why in a second. But for now, let's pretend that's the right answer. So that's all it is, right? It's just log of 50. You put in you hit the log button, you type 50, you hit enter, or if you're on a scientific calculator, you type 50, you hit the log button, right? And that should do it. And we know that 3 to the third is 27, 3 to the fourth is 81. It should be some decimal between 3 and 4, whatever that happens to be. Okay, so let's think through this. If I said 3 to the x is equal to 200, how do we solve that? We're going to do the same thing. We're going to do log on both sides. I do log on one side to undo over here, but if I do it to one side, I've got to do it to the other. So if I apply this process to both sides, log of exponential, they cancel out, they undo each other, and x is equal to log of 200. Okay, well, let me ask a stupid question. Real stupid question. If this is how we get the answer to 3 to the x equals 200, what if I asked 2 to the x equals 200? Wouldn't I do the same thing? Wouldn't I say log of this exponential is equal to log of the other side? And I will conclude that x equals log 200. That seems to be where I'm getting at, right? That seems to be my whole explanation. But there's a problem, isn't there? Can these questions really have the same answer? 3 to the x and 2 to the x are not, you're not going to put the same exponent in, the same power to make these things equal 200. There's no way that these two things are the same. And the reason why is because every logarithm is tied to a specific base. So log base b of x is the inverse to b to the x, which is to say log base b of b to the x is equal to x. And also, if we did in the other direction, it would be true as well. So b to the log base b of x is equal to x. Okay, wait, what? What's he talking about? What's this base b thing? Well, what we're going to do is we're just going to say this is the inverse for 3 to the x. So we're going to put a little 3 here to say, oh, by the way, this is the logarithm for 3, right? We've called all these other things exponentials. There's a whole class of them. There's 2 to the x and 3 to the x and 10 to the x and 5 to the x and whatever other number you can come up with to the x. Well, there's a whole class of logarithms. There's logarithm base 2 and logarithm base 3 and logarithm base 10 and all that. This is read as logarithm or just log base 3 of 3 to the x is equal to log base 3 of 50. And so logically, we have to put a little 3 here. This one is base 3 as well. It will have a base 3 logarithm. And log of a 2 to the x then is going to have base 2. So let's do one more example, and then I'm going to talk about how to put that into your calculator. So what if we said that we had 5 to the x is equal to 555? All right, so let's think about this. We have ourselves an exponential function. We need to undo it. How do we undo an exponential function? We use a logarithm. So therefore, we're going to need to do a log on both sides. Once we do the log on both sides, we have to go, oh, but what was the base of our exponent? It was a 5. Therefore, the base of our logarithm should also be base 5. The right side is just log 5 of 555, whatever this is equal to. The left side, however, just like this expression right here, with, in this case, b equals 5, equals x. So x is, the answer to our question is log base 5 of 555. And that's it. That's the whole thing. Now, we have to talk about how to put this into the calculator, because this is something that may depend on who you are and what kind of calculator you have. So, to put this into a calculator, in general, to use this on a calculator, you're going to need to do the following. You're going to need to do the log of the inside number, meaning using the LOG button, and then divided by the log of the base. And when I say log in this case, I mean the LOG button that's on the front of the calculator. What we are actually doing is using something called the change of base formula. And so if you've got an old school scientific calculator or something that's not very fancy, you are going to need to do this. And this is not pretty, because you may have to end up using the memory function and things like that. The good news is, if you have a graphing calculator that is not particularly old, like mine is, I have a TI-83. If you have a graphing calculator, it probably has a feature to input this expression directly. And in particular, on a TI-84, which is what, in my experience, most students in this area are using, you reach that by entering the math menu. The math menu is down the left side, right under the second and alpha buttons is math. You're going to scroll to the bottom, or hit up once to go to the bottom, and pick log base. If you pick log base, it will give you something that basically looks like this. And now you go, oh, well, that's easy enough. I just have to fill in the two boxes with what I want. In this case, you go 5 and 555. And so let's see what this is equal to. Unfortunately, I have an old school calculator that I have to do the change of base version, but I find that in this case, x equals 3.926. And I'm going to write 3 decimal places. Your teacher might only require 2, but I'm going to consistently write 3. So x equals 3.926. All right, what are these other ones equal to? Log 200 divided by log of 2. This is x equals 7.644. If I did instead with log 3 for the previous question, this is x equals 4.823. And the top one, the very first one we did with the 50, is x equals 3.561. Okay, so this is how I encourage you to do logarithms. It's not the only way I've seen it taught. If you are watching this and you're going, but this isn't how my teacher did it. Yeah, your teacher is doing it a really confusing way, which is to say they're talking about, oh, well, if you have 6 to the x equals 300, then all you have to do is write log base 6 of 300 equals x. Oh, okay, sure, but why? Oh, because you put this number here and you bring this number over here and you put this down here and presto changeo, there you go. That's how you do it. Oh, okay. But why? Like, how am I supposed to remember that? Well, well, it's because when you have b to the x is equal to c, then you just write log base b of c is equal to x. And that's the formula. Okay, hands up. How many people actually find that easier to remember than going, let me do something to both sides, which is exactly what you've been doing since you first learned about variables, right? Apply a process to both sides. Apply that process to both sides and then simplify. Log base 6 of 6 to the x is equal to x. And this is the takeaway, is that this is how you get x. It's equal to that, which incidentally, I can now go to a calculator and find out what that's equal to. And apparently, in this case, that happens to be equal to 3.183. So for those of you who don't like to use up a lot of space on your paper, you like to squish things into tiny spaces, guess what? You still only needed one line, other than copying the question down. You did have to insert this log 6 thing in the front, but that's it. That's the whole question. If you're the more studious type, you're probably going to write this first, and now you've got it in 3 lines total. And that is how you solve logarithmic expressions. That is the whole deal with this. And so when you have something that is raised to a power, you should be able to solve it. So let's practice real quick. So let's say we have 8 to the x is equal to 157. Let's say that we have 3 to the 2x is equal to 15,000. And let's say that we have 11 to the x is equal to 0.00034. All right, so we need to solve each of these. Let's remember that in each of these cases, we've got an exponential expression. We've got a variable in our exponent. So we are going to need to use a logarithm to solve this. We're going to need to do log of 8 to the x is equal to log of 157. What is the base of our exponent? 8. So what should the base on our logarithm be? Also 8. Over here, same deal. We're going to do log base 3 of 3 to the 2x is equal to log base 3 of 15,000. Yes, I didn't solve the first question completely yet. We're going to do each of these together in the same step. 11 to the x, log base 11 of 11 to the x. You can actually put whatever you want for the base of the logarithm. It can be a fraction, it can be a decimal, it cannot be a negative number. There are issues with that. And we'll talk about that when we get into graphing in our next video. But this is basically how we're going to do this first step. Now, log base 8 of 8 to the x, what is that equal to? Remember, these are opposite processes. So what is the left side of this equation now equal to? X. Log base 8 of 8 to the, they cancel out. And this right side, we put into our calculator. Log 157 divided by log of 8 is 2.432. All right, what is the left side of this equal to? If you said x, well, you got the right idea, but not quite, because in this case, our exponent is not x, it's 2x. But the right side is equal to whatever it's equal to, which again, we go to the calculator. There is no way to do this by hand. But in this case, we've got an extra step because we got to resolve the 2x, so we then divide by 2, and x is equal to 4.376. 11, 11, okay, these match, it cancels out. X equals log of 0.0034 divided by log of 11. Again, if you're not clear on what I'm doing to push the buttons, on my old TI-83, which doesn't have log base, I'm literally typing in this. And you can do that on contemporary calculators if you don't feel like going through the menus. Or you can just do log base and put the 11 down below and put the number we're putting up here above. And the number in this case is negative 2.370. It's negative. Oh, that's weird. Why is it negative? Can you tell me why it's negative? Can you think about why would this be negative? Think about it. 11 to the first is 11. 11 to the second is 121. 11 to the 0, though, what is any number to the 0 power? It's 1, right? What's 11 to the negative first? 1 over 11. 11 to the negative 2 is 1 over 11 squared, or in other words, 1 over 121. We have a fractional number. We have a decimal that is smaller than 1. So does it make sense that we have a negative exponent? Yeah, actually it does. Okay. Two random little bits of terminology I'm going to throw out here just in case your teacher brings them up. These are super not important pieces of information. The number 2 in 2.432 is called the abscissa, and the 432 part is called the mantissa. I don't know in what world you actually need to know this information, but I have seen teachers use the terminology, so I want to at least throw that out there in case it becomes relevant. Um, there's a lot more that we can say about these. The only thing that I'm going to throw out here is one last thought, and that is, what if we wanted to go backwards? What if we had a logarithm with an x inside of it? How do we solve this? Okay, so the whole deal with a logarithm was it was the inverse to an exponential. It undid the exponential. So how do we find the inverse to a logarithm now to get this x out of the logarithm? We got to undo the log. What's going to undo a log? Well, inverse to multiplication is division and division is multiplication. Addition and subtraction cancel each other out. Squaring and square root do. It seems like it would make sense that we would need an exponential. Well, the thing that we're playing with in an exponential always goes in the top. So this stuff needs to be in the top part of an exponential expression, and the base of our logarithm is 2, so that suggests that we need to do 2 to the on both sides. So now this is 2 to the log base 2 of x is equal to 2 to the 6th. That 2 is a little out of position to make that look like an exponent there. Maybe that makes it a little clearer what I'm trying to do. So 2 to the log base 2 of x. Once again, these are inverse processes. So what is the left side equal to now? X. And what's the right side equal to? 2 to the 6th, which we can figure out. We can count our hands 2, 4, 8, 16, 32, 64. If you didn't already know that one. So x is 64. So if we need to solve a logarithm, it's just do an exponential on both sides, and that's all it is. And whatever base you have of your logarithm, that's the base of your exponent. And that's it. That is the entire deal with solving logarithms and converting back and forth. If you have something where it's Oh, write this in logarithmic form, like 3 to the fifth equals 243. All right, just treat the 5 like it's your variable and go, oh, I need to do log base 3 on both sides. Log base 3 of 3 to the fifth is log base 3 of 243. And by the way, this reduces to 5 because the log base 3 and the 3 to the cancel out, and it's log base 3 of 243. Please, 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 I'm begging you, do it this way and not this way. The presto changeo route does not make any sense, and you will never remember it later. Maybe you'll remember it long enough to finish this chapter and take the test, but logarithms are a relevant topic. They are actually super important. They tie into one of what I would consider to be the most important topics that you will learn in all of high school math, perhaps in just all of high school. So, in that case, I would strongly encourage that you do not completely dismiss exponentials and logs. They are important and they will be something that you will need to know for one very specific topic, if nothing else. So, please don't use the, oh, I'll cram it for the test routine here. This presto changeo shell game, which one is the ball under type movement where you just shift things around and, oh, see, here it is. I don't like this. I do not like it at all. I find that no student ever does well with this. I strongly encourage you to make it a process, to do the process to both sides. And if you do that, then logarithms should not actually be very hard. For Algebra 2 students in general, this tends to be the hardest topic in the entire year most of the time. And it doesn't have to be. It's really not a big deal if you do it this way. So please, I'm asking you, do the process to both sides and not the shift around. Thank you.